Today we are going to learn the final integration method in BC Calculus called improper integrals. And we'll talk more about it in just a minute. Basically, it has to do with approaching infinity. So when I ask you about a graph and ask you what it's doing as it approaches infinity, where do you look? Where do you look on the graph? Where x is approaching infinity, you look on which end? The left side or the right side?
Right.
The right side. Okay? So we're going to be looking at limits that approach infinity, not of graphs, but of areas. Okay? So let's start out by reading the scenario right here. Suppose you were driving along the highway at 100 feet per second, which is approximately 68 miles an hour. At time t equals 0, you take your foot off the accelerator and let the car coast, and assume that the road is flat. Okay? Your velocity is given by this function here. V of t equals 100 e to the negative 0.1 t, where t is in seconds and v of t is in feet per second. So it is slowing down. This is your velocity. So what I want to do now is take your calculator, and I want you to go into y equals and type in this velocity function for me. So you're going to have y equals 100 and then e to the negative 0.1x. You're going to get it. There's a good picture. 100e to the negative 0.1x. Now this is the velocity graph. We need to set the window for this. It is not a zoom 4 or zoom 6 because velocity cannot be negative. Okay? So let's push the window key now. X is time. What is the minimum time this car is going? 0. So 0 is your minimum for X. If your car was coasting along, how many seconds do you think it would be until it stopped? 10 or more?
10. What does coasting mean?
If you were going 68 miles an hour and you just take your foot off the brake, how long is it going to take you to slow down to a stop?
Like a lot of time.
A lot of time? I mean, if you hit the brakes, it takes you only about 8 seconds to stop.
Oh.
But if you're coasting to a stop, it's going to take you a lot longer. So I'm going to say 100 seconds. That's almost 2 minutes. Okay? Now the scale number is, if you were going to draw the graph yourself, how far apart would you put the tick marks if you're going from 0 to 100? 10s. 10 sounds great. Now y is your velocity. What is your minimum velocity? 0, because you're never going to go into negative velocity, right? Now what is the maximum velocity in this scenario?
60.
Okay, we're doing it in feet per second. So it says up here, we're going at 100 feet per second. So we're going to do our scale of 10 again. So it's 100 in both directions, basically. Okay? Now push graph. Do not push zoom or you're going to lose all your settings. Push graph. Okay. If I asked you what the limit as x approaches infinity of that graph is, what would you tell me?
0.
It is 0. What are you looking at on the graph to tell me that answer? Where the x-axis is going. Notice the graph is going down and it's headed towards 0. Okay? It may get there, it may not. It looks like it's headed to 0. Do you agree with that statement? Okay. Those are the kind of limits we need to do that we know how to do already. But what we're going to talk about today is we're going to talk about distance. Now listen to my question. If I give you a velocity function and I want you to tell me something about the distance, are you going to take the derivative or the antiderivative? To go from velocity to distance. Which one is that? That's antiderivative. An antiderivative is like integral. And what is the integral going to tell me about this graph? It's going to tell me the area under the curve. Okay? So my question is, as x approaches infinity, what's happening to the area? Is it just getting bigger and bigger forever? Does it look like that area as I go left is going to just keep getting bigger and bigger?
No.
If it's getting really tiny on the end? Probably not. What we want to know is that area approaching a value?
Yes.
Is it getting close to a number? Not necessarily getting there, because that's what a limit is. In other words, are those values on the end negligible? Do they not affect the area that much? Okay? That's what an improper integral is all about. We know that the function itself approaches 0, but what does the area do? And that's what we're going to solve for today. So, according to the model, we're back on the page, the velocity approaches 0 as time approaches infinity. You just told me that. But never does it equal 0. It will never get to 0. It's going to get close. So, if you take this problem and you take the limit and you do the math, you will have 100 over e to the infinity. Now, e to the infinity is infinity. Okay, it's huge. So a number over infinity, we discussed earlier, is equal to 0, just like we wrote on the board over there. Number over infinity is 0. So would the distance approach a value, or would the area approach a value, or is it going to increase without bound? So we're going to learn 3 new vocabulary words today: improper integral, convergent, and divergent. And convergent and divergent are going to be huge for the rest of this semester. You're going to know those words, if you don't already, like crazy. You're going to use them a lot, okay? An improper integral is an integral where either the top or the bottom limit of integration is not a number, it's infinity. Okay? So you're going to have an integral that goes from a to infinity, or you're going to have an integral that goes from negative infinity to b. Okay? And we're going to calculate what that integral is. Well, integral, you usually just plug in the numbers and calculate the answer. But what do you do when it's infinity? How do you solve it? This is the procedure. Put a big star right here. This is big right here. This is the way you do the problem. When you have the upper limit as infinity, that's your b number. If you see a problem that looks like this, you take the infinity off and replace it with a b, and then you take the limit as b approaches infinity. Are you following what I'm saying? The infinity turns into a b, and then you take the limit as b approaches infinity. Because we can work with a b, we just can't work with an infinity up there. On the flip side, if the bottom a is infinity, then you change the bottom to an a, and then say that the limit as a approaches negative infinity. And then work the problem. Okay? So in just a minute, I'm going to show you mathematically how that works and what's going on. Now the next part is the one that's really kind of difficult to understand, so I need you to listen very carefully. An improper integral converges to a number if the limit shown above is finite. So in other words, after you do all the math, if you get a number answer, pi, 2, 3, whatever, if you get a number answer, your limit is convergent. Your area is convergent. Otherwise, if the limit is infinite, the integral diverges. So when you're done, if your answer is infinity, it diverges. And so from this point forward, as you're doing these problems, you're going to write down convergent or divergent. Okay? So the easy way to remember it is this. If your answer is infinity, it's divergent. Everything else is convergent. Okay? Everything else is convergent. Now, listen very carefully to this part. I'm changing colors. An improper integral cannot be convergent unless the limit of the inner function of the integral is 0. The inner function has to approach 0, or there is no way that the graph can converge. If the inner function of the integral does not approach 0, it is not going to converge. Okay? Now, do you understand what I'm saying or no? You're kind of shaky on this. Are we kind of shaky on this? Okay. I wrote this on paper for the other class, and you might be able to squeeze it in the top and just kind of look at this. Now, the f of x is like the velocity. When we looked at this graph, Is the velocity approaching 0? Yes. So this one could converge. So basically, if the velocity approaches 0, let me do it a different way. I'm going to have to take this out. Start over. Okay. If the limit as x approaches infinity of the velocity is 0, it could converge or it could diverge. I don't know which one it's going to do. But if the limit as x approaches infinity of the velocity is infinity, it's an automatic diverge. This is what the distance will do.
So basically the one on the top, it could be a number or it could be infinity.
Right.
And then we need
The improper integral could be a number or it could be infinity. This is a situation, let me just sketch this. If your graph goes to 0, there is a chance that that area could converge. In other words, the area could approach a number but not quite get there. Okay? But if a graph approaches infinity, like that one, is there any way as I move out and calculate area that the area could approach a number? The area is just going to explode in size, isn't it? So this is saying if the velocity graph has a limit of infinity, it has to diverge because there's no way that you're going to get a number answer for that area. That area is just going to get monstrously huge. Does that make sense? Yes? No? And ask questions.
Does diverge have like an alternative meaning that we can like relate it to? Does it mean to like?
Yes. Diverge means to go off the beaten path.
So I mean,
So it's kind of the thing. Converge means to come together. Diverge means to go off the beaten path. Yes, sir.
So we wouldn't have to do the whole integral thing if it just diverges?
Yes. You have caught the point. If I look at the velocity and I see that the limit is infinity, I won't go through and do the whole integral because I know automatically that the answer is going to be infinity and it's going to diverge. Do you follow what I'm saying? So you basically throw out the problem. You don't have to do it. Okay? Yes, ma'am.
If we're kind of confused now, will we just be like, will we understand it better whenever we do the problem?
I think so. And I think the more you think about it, it's going to make sense. Even if you don't completely understand the graphs and the things like that, you can still do the math for this problem. It took my brain a while to understand it. But but I could still do the math. You know what I'm saying? Even if you don't conceptually understand everything. All right? So remember that we're looking for the area under the curve, but you're not stopping at a certain point. You're going out forever. Now, is that area approaching a number or is it not? That's the question today. Okay? So let's take a look at this again. The graph to the right shows the velocity function described above. The distance the car travels between 0 and B is shaded in. Okay? So what I want you to do now is take your calculator and go to the home screen, and I want you to find the distance the car traveled in 10 seconds. So if I know the velocity graph and I want to find distance, I should do a what? A derivative or an antiderivative? Antiderivative. So that means I need to do a math 9. So if I want it for the first 10 seconds, 0 to 10, very good. So put it in 0 to 10, and then y1 dx equals 632, okay? And it gives me that number right here, 632 feet. So in this scenario, you're driving along 68 miles an hour, run, run, run. All of a sudden you take your foot off the accelerator on a flat, like a jet runway. You're just going on there. After 10 seconds, you have gone 632 feet. Okay? The question is there a maximum distance you will go? You will never go past this far. That's what we want to find. Okay? As B approaches infinity, the velocity does approach 0. We already figured that out. We looked at the graph and we saw that the velocity approaches 0. So over here in this box, they do the math to actually figure out what the integral is going to be, because if the velocity approaches 0, our two choices, it could give us a number or it could give us an infinity. So take a look at this box. This is stuff you know how to do. This is from before, okay? You have the integral from 0 to b, pretend like b is a number, of that function right there. 100e to the negative 0.1x. Now, what kind of integral is that? Can I do a u to u to this? It's a definite integral, yes. But how many x's do you, how many t's do you see in there, not including the dt? Just one. So this is back to easy kinds of integrals. So u would be the exponent, and du would be what? What's the derivative of that exponent up there? Negative 0.1. Okay, so we'd have to put a negative 0.1 inside, which is 1/10, right? So what would you have to put outside? The reciprocal of that, which would be negative 10. So that's why this 100 turns into negative 1,000. It was very hard to clean up this PDF. It was not doing what I wanted it to, so that's why there's random brackets in here, so I apologize. So I now have this integral, and we plug in 0 to b, and I'm going to do that down here. I'm going to add a step. So plug a b into here. That would be, so we have negative 1,000, plugging in the b, e to the negative 0.1b minus negative 1,000 e to the 0. So I plugged in the b, and I plugged in the 0. Now this becomes plus plus. Agreed? Okay. Tell me real quickly, what is e to the 0? 1. So this last term is just 1,000. And this would be, with the negative exponent, it goes on the bottom. Negative 1,000 over e to the 0.1b.
That's a b.
That's a b. Because that upper limit is a b.
No, the exponent.
Up here it was a t to start, and here it's a t as well. But then I'm starting to plug in the limits of integration, and the t turned into the b.
Oh,
Okay? Now, do you see that what I wrote here is the same thing as they wrote there? The terms are just flipped. Okay? All right. So what you do is you replace the infinity with a b. Okay? And you just do it like you know how. So now I have b's in my answer. But what we have to do now is take the limit as b approaches infinity. Yes?
For that part that you just wrote,
Uh-huh.
where did the minus negative 1,000 e to the 0 come? Oh, I see now.
Plugging in the lower limit.
Mhm.
Okay? Are you with me? So what I'm going to do now is take this thing I just got that they wrote, and I'm going to take the limit as b approaches infinity of 1,000 minus 1,000 over e to the 0.1b. I turned it around their way. I'm doing the limit as b approaches infinity. Now I'm going to cover up the fraction with my band-aided finger. What is the limit as b approaches infinity of 1,000? I'm hearing 1,000 and I'm hearing infinity. Okay?
Infinity
Think about it graphically. What does the graph of y equals 1,000 look like?
of line.
Like this, flat line, right? Looks just like that. As I go all the way to the right, what's the y value going to be? The y value. 1,000. It's always going to be 1,000, isn't it? So the limit as b approaches infinity of 1,000 is 1,000. This equals 1,000, right? Okay? But if I plug infinity into this exponent for b, just looking at the fraction part, I would have negative 1,000 over infinity. and that is 0. That has a limit of 0. So the answer is 1,000. So this improper integral converges because I got a number answer. It converges to 1,000. So if I could calculate the area from 0 forever under that graph up there, the area would never surpass 1,000. Okay? Its limit is 1,000. Which means in your car would never go more than 1,000 feet down the road. That's what it's saying. Okay? Questions? Yes, ma'am.
How did you get the 0? I'm confused.
Okay.
E.
B is infinity. Replace the exponent with b. Replace the b with infinity. So you have e to the infinity power.
Oh, so you have a number over infinity, which is 0.
Correct.
Oh, okay.
Okay. You have a number over infinity, which is 0. Yes. All right. Any other questions? So please write the words converge right here. That one converges because I got a number answer. So let's take a look at the bottom of this. We're going to change our function to this. 400 over t plus 4. Does this graph and this graph look kind of similar?
Yes.
Yeah. This one's not going down as fast. Is this graph's limit itself of the graph, is the graph approaching 0 as you go to the right? Is the graph look like it's approaching 0 as you go to the right? Yes. But over here, if you do the math, look at this problem. Let's actually go ahead and do the math. We got time to do this. So we have the integral from 0 to b of 400 over t plus 4 dt. You may want to write this down and follow along, or just watch me. It's up to you. I'm going to do exactly what they did in the box, but I'm going to add some more steps. Is the top the derivative of the bottom? Every time you see a fraction, that's what you ask yourself.
No.
Is the top the derivative of the bottom? But can I make it the top? Can I make the top the derivative of the bottom?
Yes.
Yeah. So what do I do with that 400?
Pull it out.
Pull it out. Pull it outside. So let's mark that out, put it outside, and what's in its place? A 1. Now is the top the derivative of the bottom? Yes. So this is now 400. So what is that going to equal? What kind of problem? We did this all day yesterday. ln. Absolute value of t plus 4 from 0 to b. So what we're doing now, what are we doing? We are finding the limit of the area. Let's see if as we go out to infinity, is the area going to converge? Is it going to get really close to a number, or is it just going to keep getting bigger and bigger and bigger? All right, so let's plug it in. So this would be 400 ln absolute value of b plus 4 minus, be careful, I know you're plugging in 0, that doesn't mean it's going to be 0. 400 ln of 0 plus 4, which is 4.
You don't add a plus C?
No, whenever you plug in values, you don't put plus c. Okay? Now, think about yesterday. When the numbers in front of ln's are the same, what do? We put this into a fraction. So this would be 400 ln absolute value of b plus 4 over 4. Okay, so that's the function with b's in it. So now we want to know what is the limit as b approaches infinity of that. Let's see. So we're going to come over here. I'm going to change colors because I'm changing gears. I'm going to take the limit as b approaches infinity of 400 ln absolute value b plus 4 over 4. This is not a L'Hopital's problem. There's no fraction with b's on top and bottom. This is just a plug-in infinity. So I have 400 ln of infinity. You all agree with that? If I take infinity and add 4 and divide by 4, it's still huge. Okay? So, do you remember what ln looks like? take your calculator real quickly. Go to y equals and type in ln of x. And do a zoom 4, please. Okay. As x approaches infinity, what is y doing? Is it approaching a number or is it approaching infinity?
0.
As you go to the right, what's that graph doing?
Oh.
It's going up and up and up and up and up and up and up. It's not flattening out at 2. It kind of looks like it is. If you back the graph up, you'll see it's just continuing to climb slowly. So the limit of ln as x approaches infinity is infinity. So that means that this right here is infinity, and infinity times 400 is still infinity. So this one diverges because I got infinity. The area under that graph will never level out. The area won't. It's just going to keep getting bigger and bigger and bigger and bigger and bigger. You know how they say that an object in motion tends to stay in motion unless acted upon by an outside force?
Yes.
I remember seeing a video a long time ago talking about like a hockey puck. Thinking about a hockey puck going at a velocity just forever and ever and ever. It's never going to slow down. This is a kind of situation of a divergent scenario. It just never stops. It never gets there. Okay? How are you doing? So? Okay? All right, let's move on to the back of this page. We can do a little bit more. So, look at the top of this page on the back. Everybody there? It says graph this function. Just put this in your calculator and see whether or not you think it could converge, the graph itself. So we're going to go to the y equals. We're going to type in, oops, clear that out, x squared e to the negative x. And set the window the way it is right here. It's 0 to 10 on the x. So we go to window, 0 to 10. Now, I need you to go up to 0.6 or you're not going to see the whole graph. So 0, whoops, 0, 0.6, and 0.1. You can't see that very well. Here we go. 0 to 10 and 1. 0 to 0.6 and 0.1. Okay, then push graph. Just take a look at the graph. Yes, ma'am.
If we were doing this by ourselves, how would we know to change the scale to those numbers?
You would have to just play with the graph a little bit. They would tell you in a situation like this what to do. Okay, but honestly, we're going to be doing more of the problems without looking at a graph than with looking at a graph. Okay, so sketch that in the box that's out to the side on your paper. What does that look like to you? Does that look like a slide that you went on as a child at the playground? Maybe. So it goes up to 0.6 and then comes back down and does something like that. Could the limit, okay, first of all, what does the limit equal as you approach infinity? Does it equal infinity or does it equal 0? It equals 0, doesn't it? Isn't this thing getting closer and closer to 0? So, could the area converge? Yes. If this limit is 0, the limit of the graph itself is 0, the area could converge. So the answer is yes, because the limit as x approaches infinity of f of x equals 0. So, now that we know that it's a maybe, we can continue the problem. I want to find the integral from 0 to b of this. So, look at this problem. How many x's do you see in there besides the dx? I see 2, and they are multiplied together. So either one is the derivative of the other, or we're going to have to do integration by parts. Is one of those the derivative of the other one? No. Okay. Now we learned when we did integration by parts a couple days ago, a couple ways to do this. Do either one of those two functions loop? E does. E loops, doesn't it? You do derivative or integral, same thing over and over again. But x goes down to 0. So whenever you have a looper with an x, it is the table method to work. Okay, a looper with an x is the table method. So in this empty space up here, we're going to make our table. You need to push to write sine u and dv. Sine u and dv. Let's review how to do this. Who remembers what the signs do with the table method? Plus, minus, plus, minus. So plus, minus, plus, minus. Which of the two functions goes in the u column? The x one does. The one that's just x. So in this case, it's x squared. So x squared goes in the u column. The looper goes in dv. So e to the negative x dx. Actually, I don't need the dx. I'm sorry. Shouldn't have written that down. Okay. What do you do down the u column? Take the derivative until you get to 0. So the derivative of x squared is? Whose derivative is? 2. Whose derivative is 0. There you go. Okay. Now down the dv column, we do antiderivatives. So how do you take the antiderivative of an e? Copy and paste. So we write e to the negative x. But then we got to think what has to go in front of that so that when I take its derivative, the negative doesn't show up. A negative sign right there. So it's negative e to the negative x. Okay? So for the antiderivative again, we do another e to the negative x. But what sign is it going to be? Positive. And then for the last one, we do another e to the negative x, and it is negative. Okay. So now we connect them like we're supposed to. The sign in the u, remember, goes straight across. But the u to the dv goes down. Down to the dv. So now we copy down what the answer is. So that would be negative x squared, move over a ways, negative x squared, e to the negative x. And then the next triple is a negative 2x e to the negative x. And the last one is a minus 2 e to the negative x. Bracket 0 to b. We used to put plus c. This is not a plus c problem because it's a definite integral. But before I start plugging that in, that's a lot of stuff. Can I factor that at all? It would really make things a lot easier. I can take out the e to the negative x, and that will honestly make things better. So e to the negative x times negative x squared minus 2x minus 2 from 0 to b. And I'm going to have to move over here. And anything with a negative exponent goes where? Underneath. So this will be negative x squared minus 2x minus 2 over e to the x from 0 to b. Now I'm going to run into letter c, and that's okay. I'll have enough room to do it as well. So which of the two limits do we plug in first again? The b or the 0? The b. So we're just going to write the problem again with b. So it'd be negative b squared minus 2b minus 2 over e to the b minus, if I plug 0 into the top, what am I going to get? Negative 2 over e to the 0. And e to the 0 is what? 1. So it's just negative 2 minus negative 2, which I am now going to make plus plus. Okay, so that's the answer to B, to part B. Now they want you to take the limit as b approaches infinity of what we just found. So we're going to come over here and we're going to do the limit as b approaches infinity of negative b squared minus 2b minus 2 over e to the b plus 2. Now, the AP test does not require that you show all the steps to get from here to what its limit's going to be. Because a lot of it you can do in your head. Okay? If I plug in infinity right now just to the fraction part, am I going to get infinity over infinity? Yes. So then I would use L'Hopital's rule to take the derivative of the top and then the bottom. What's the top's derivative going to be?
Negative
Minus 2. And the bottom will still be e to the b. Okay? What if I keep doing that procedure over and over again, what will the derivative of the top eventually be?
0.
It'll be 0. Well, actually, right before that, it'll end up being a constant before it's 0. So if you have a number over e to the infinity, a number over infinity approaches what? 0. This one is going to have a limit of 0. The fraction will. Because L'Hopital's will make the top eventually constant out before the bottom does. Does that make sense? Mm-hmm. The top will eventually constant out before the bottom. So that's 0. But the limit as b approaches infinity of 2, we did one just like that before our break. It's just 2. So the answer to this one is 2. Now let me say one more time what that answer means. That answer is the area of that hump all the way out to infinity under the curve. It's never going to get any bigger than 2 total. Okay? 2 square units. All right. Questions? Okay, we're going to jump down, skip number 3, and go on to number 4. Let's do just a regular problem. No calculator at all. We're just going to work it out. All right? So we have here, find the limit, the integral from 0 to infinity under e to the negative x dx. So what we're going to do is we're going to write it as a limit. So we write limit as b approaches infinity, integral 0 to b of e to the negative x dx. So just like I showed you on the front, using the formula that we starred, we change the infinity symbol to a b and write a limit in front of it. The limit as b approaches infinity. Okay, every time, now that you've got so many different integral methods, first thing you should do when you see an integral is to count the x's, not including dx. How many x's do you see? 1. If you see only 1, that means it's going to be an old-fashioned u substitution or just a regular integral. Okay? Have we done e to the negative x already today? I tell you that we did it about 5 minutes ago. Look at your table at the top of the page. Did we take the antiderivative of e to the negative x? Yes, we did. So we can do this one really quickly. So what we do, go to the next line, write your limit. Limit must be written until you plug in infinity. The antiderivative of e to the negative x is negative e to the negative x, bracket 0 to b. So this equals the limit as b approaches infinity of negative e to the negative b minus negative e to the 0. So I took the antiderivative, then I plugged in the b and the 0. And now I need to take the limit. Okay? When you have a limit approaching infinity, usually it means you've got a function over a function. Is that what that is? Is negative e to the negative b a function over a function? Is it? It's got a negative exponent, so I need to move it down. So this will be the limit as b approaches infinity of negative 1 over e to the b plus, what is e to the 0 again? 1. Okay, that's the function I'm taking the limit of. Okay? If I plug infinity into the denominator, I'm going to have 1 over infinity. And what does 1 over infinity simplify to be? What does it approach? It's 0. So this is going to be 0 plus 1, which is 1, and it does converge. So do you understand the process? You may not understand mathematically what it's doing on the graphs or anything, but if you can go through the steps until your brain catches up with it, you'll be fine. Yes, sir?
Okay, yeah, I raised my hand just to like go over the process quick. So
Okay.
I'm just trying to get straight. So we turn it into a limit. We turn the integral into a limit.
We turn it, and then what do we do next?
Next we integrate it.
We integrated it, exactly.
Right? And then after we integrate it, we write out we write out that integrated.
Right, you plug in the 0 and the b,
Right.
right here.
We plug them in, and then after we plug them in, we just get our answer.
You just take the limit, yes.
Right.
Yes, remembering those 3 facts that we gave you at the beginning of class. Okay? All right, are we good? We're going to do one more together, and then you're going to try one, and then we're going to be done for today. Okay? Take a look at this function right here. It goes from negative infinity to positive infinity. That's a little weird. So what we're going to do is, we're going to do it in a different color, just to be fun. We're going to do the limit, and we're going to just pick a letter this time. B approaches infinity from negative b to positive b. Now do you see that that works? I don't have to do 2 separate integrals. I could just do one big one and pick one letter and make it negative and positive. Now this, remember, stays the same on the inside until we figure out what it is. 1 over x squared plus 1 dx. Yes, ma'am?
Does B just represent infinity or any number?
B represents infinity, because B is approaching infinity. Okay, so how many x's do you see? 1 that's squared, okay? So it's fraction. Is the top the derivative of the bottom? No. And I can't make it that way because it's missing an x, agreed? Okay, so if that was the case, what we did yesterday was take anything on the bottom that's a polynomial and factored it. Can we factor x squared plus 1? How does it factor?
X minus 1. No. Wouldn't that be
You can't factor that.
Is it
But then you would get a 2.
Isn't it x minus 1?
X minus 1 squared would be x squared minus 2x plus 1.
You would get another x. So it would be x squared plus x plus 1.
Right. So the answer to the question, after you've now thought about it for a while, is no, you can't factor this. If it was x squared minus 1, it would work, but it's not. So if it's not if the top's not the derivative of the bottom and it's not going to do partial fractions, it's got to be something else. So I'm going to pull out the flip chart, and it is. I want you to take a look at right there. One of those things on that page is your antiderivative. And it's not over here. It's this one right here. Do you see it? 1 over 1 plus u squared du, in this case it's x squared dx, is tangent inverse. So we go straight to the answer. So this is going to be the limit as b approaches infinity of tangent inverse of x from negative b to b. So we figured out its tangent inverse. What is my next step to do? Plug in the negative b and b. So this will be the limit as b approaches infinity of tan inverse of b minus tan inverse of negative b. Now what? Now don't make the mistake of thinking tan inverse means 1 over tangent. It's not. You can't. This is the one instance where negative 1 exponent does not mean put it on the bottom. Okay? So what I want to do is take a look at the graph of tan inverse, because probably you haven't seen this graph since pre-cal. Okay, so take your calculator, please. Do you know how to get tan inverse on your calculator? How do you do it? Second tangent. So second tangent of x. And we're going to do what's called a zoom 7. Zoom 7 is made specifically for trig functions. Goes from negative 2 pi to 2 pi. There is tan inverse. Do you see that that is somehow related to tangent?
Yeah.
You remember what tangent looks like? It goes up, asymptote, up, asymptote, up, asymptote. Okay. Can you tell me where the asymptotes were on tangent?
Negative.
At what?
Was it
Pi over 2.
It was a multiple of pi. Say what you said again?
Pi over 2.
Pi over 2. And then what was the next one? 3 pi over 2. Odd multiples of pi over 2. Okay? Then what about on the other side of the y-axis?
It's just the negative.
It's just the negatives. Okay? So we're on the one that's in the middle. This side was negative pi over 2. And this side was positive pi over 2, right? So what's happened here is that instead of the asymptotes being like this, they're now like this. So what is my upper asymptote? It's at pi over 2. The upper asymptote is at pi over 2. And the lower asymptote is at negative pi over 2. So, as I approach infinity, positive infinity, this graph is approaching pi over 2. So the answer to this one, tan inverse of infinity, is pi over 2. And then on the other one, the bottom side is approaching negative pi over 2. So this means it's going to be minus negative pi over 2 plus plus. So that equals 2 pi over 2, which reduces to pi. So what does all this pi stuff mean? Let me show you. Okay, this was our function, 1 over x squared plus 1. Zoom 4. Look at the graph. See how that graph just has a little hill in the middle? And it kind of goes out on the sides? Do you see that both sides are approaching 0? This one does converge. So it's saying the area under that hill, all the way out to infinity, will be no bigger than pi. That's what we just figured out. It will be no bigger than pi. So this area converges. What do you think? Questions? Okay, right now, to wrap things up, I want you to do number 5. Look at number 5. Okay, limit as b approaches infinity of integral from 1 to b of x to the negative 2 dx. Limit b approaches infinity. Parentheses x to the negative 1, 1 to b. Limit b approaches infinity. Negative 1 over b minus negative 1 over 1 plus plus. So that's going to be 0 plus 1, which is 1. And it does converge. All right, a second type of improper integral is one that is explained in this paragraph right here. So read along with me. It says a second type of improper integral is in the form of the integral from a to b of f of x dx. Do you see an infinity on that integral anywhere? No. But what's happening is that f is discontinuous either at a or b or both. In other words, if you plug a or b into the function, you get undefined. Okay? It just doesn't exist there. And I'm going to do an example in a minute. And sometimes the improper integral is in the form where there's a number in between where it's discontinuous. And you would have to break it into 2 separate integrals. Okay? But we're going to focus only on the ones where it's one of the endpoints. Okay? So we're going to take a look at this graph right here. This is 1 over x. This is a parent function you've known for a while. I want to find, we're going to do part A only. We're going to find the area bounded by the function, the x and y axis, and the line x equals 1, which is right here. So we're talking about this piece over there. We're going to find the area of that, and we're going to see if it converges or diverges. Now, the test that we talked about earlier, where you say, as you go out to infinity, if it diverges, it's going to diverge. We're not going out to infinity anymore. That doesn't work in this scenario. You just have to do all these problems and see. There's no, I can throw it out ahead of time. You have to work the problem. So here's what we do. Here's part A. We're going to do the integral from 0 to 1 under 1 over x dx. We're going to find the area between 0 and 1 of 1 over x dx, even though this curve does not exist at 0. That thing goes up to the right forever and ever because 0 is an asymptote. So we want to see, does it converge or diverge? So what we're going to do is we're going to replace, okay, first of all, do you realize that if you plugged a 0 in for x, you're going to get an undefined value? That's pretty obvious, okay? So anytime that happens, you have to replace that number with a letter. And we're going to make it a limit now. So this is the limit as a approaches 0. And we have to be specific from the left or the right. I'll come back to that in just a second. It's going to be the integral from a to 1 of 1 over x dx. I left some room because I got to put a symbol in there. Okay. You have to decide whether it's 0 from the left or 0 from the right. And there's a very easy way to do that. Okay. I'm going to use my hands as a demonstration under the camera. The limits of integration to begin with were 0 and 1. So the areas between where my thumbs are. Okay. Which side of 0 is the area?
The right.
It's the right side of 0. Agreed? So you're approaching 0 from the right. So what you have to do is think about where is that asymptote, so to speak, where is the area in relation to it. If the area is on the right, you do the limit from the right. If the area is on the left, you do the limit from the left. Okay? Are you with me? We'll do another one in a minute just to make sure you got it. Okay, so now, do you recognize this antiderivative? Do you know what it's going to be? It's going to be ln. So we're going to write limit as a approaches 0 from the right of ln absolute value of x evaluated from a to 1. Just like before, we take the antiderivative. And now, just like before, we plug the numbers in. The limit as a approaches 0 from the right of ln of 1. Now, since 1 is positive already, the absolute value of 1 is just 1. You can change it to parentheses if you want to. If you don't, it's no big deal. Minus ln absolute value of a. I'm going to go ahead and leave it in absolute value because I haven't really defined it yet. It's still a variable. So now, whenever a is approaching a number, what do you usually do to evaluate the limit? You just plug the number in, don't you? So this would be ln of 1 minus ln of the absolute value of 0, which is 0. Agreed? Okay.
Ln of 1 is 0.
The ln of 1 is 0. So I can write that this is equal to 0.
But ln of 0
Equals 1.
Does the ln of 0 equal 1? Well, let's see.
because it would be negative.
Let's see. ln of 0. Can you see my screen?
Oh,
No, you
this is
can't.
impossible.
ln of 0 is, oh no, I can't do this. You were right. ln of 0 is impossible. It doesn't exist. Why? Okay, let me show you. Here is the graph of ln of x. Look at the graph. What's the graph doing as you get close to 0? It's going down, 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 and never going to get there. So, the ln of 0 does not exist. So this limit is infinity, and it diverges. So, how do you know it's infinity? Since you plugged in a number, because you got something that doesn't exist. So you're actually doing 0 from the right, and which is actually going to negative infinity. Okay? If you're plugging in a static 0, it does not exist. But since you're talking about a limit, it's an infinity. Well, in actuality, it should be a negative infinity. But it's minus a negative. Oh, that's right. So this is minus negative infinity, which is a plus plus. There we go. So because this line goes up and up and up, and it never touches 0, the area just keeps getting bigger and bigger and bigger. And it diverges. Questions? All right, we're going to do, yes, do you have a question? Okay, we're going to do one more question. We're going to do number 10, but we need to change the limits of integration because this paper did not give us any samples of these kinds of problems. So instead of 1 to infinity, I want you to change it to 0 to 1, please. So change the limits of integration on number 10 to 0 to 1. Of 1 over the cube root of x. Same procedure we just did. Okay? If you plug in either one of those values to that integral, are you going to get an undefined? Which one's going to give me the undefined? 0 is. So what we're going to do is we're going to replace the 0. So we're going to have limit. Now because that's the a of a and b, we're going to say that a approaches 0 from which side? Right or left? 0 to 1.
Right.
Area's in the middle, so it's the right. It's on the right-hand side of 0. So it's going to be the integral from a to 1. How do I write this so I get it ready to take its antiderivative? Let's go ahead and bring it up at the same time. It's going to be x to the negative 1/3. Very good. dx. All right. So now we take the antiderivative. A approaches 0 from the right. Parentheses. What does x's power become?
2/3.
You're adding 1 to this. It is 2/3. Negative 1/3 plus 3/3 is 2/3, right? So what goes in the parentheses? 3 halves the reciprocal. Not a plus c, but a bracket, a to 1. So now we plug in the values. The limit is still there. A approaches 0 from the right. 3 halves 1 to the 2/3 minus 3 halves a to the 2/3 equals. What is 1 to the 2/3 power? 1, because 1 to any power is always 1. So that first term is going to be 3 halves. Now a is approaching 0. Can I plug 0 into this and get an answer? What is 0 to the 2/3? It is a number. It is not undefined like the last one. This is 0. And 0 times 3 halves is 0. So I get a numeric answer of 3 halves.
So convergence.
This one converges. And the area under that curve is 1.5 or 3 halves. So do you see the difference between this one and the one we did before? Because at the very end, we could plug in the 0, but before we started, we could not. So that's why this one ended up converging and the other one did not. Okay? So I'm going to say it now so that it's on the video. Remember that the first type of improper integral that we learned, we gave it a funny name. We called it an infinigral. It's an infinite integral. It has infinity somewhere. Or it could be one of these where you plug it in and it's undefined on either end. Okay? Any last minute questions?